Hello everyone, Professor Dustin here, and this video is going to be a solution for a real-life skater whiteboard. So basically this is an attempt to do a slightly better job with the model we have of a skater pulling in their arms and their speed changing by modeling the skater and their arms with shapes that we know we can study in the physics lab. So the skater's body is I0, that's going to be a disk, which is the same as a cylinder. That's going to be the same at the beginning and the end. And then it's going to have a radius of 12. That's right there. And the arms are going to be treated as point masses. So, okay, your arms are long. They're not really point masses, but you can simplify all that stuff by saying they are point masses with a distance r0, which starts at 35 centimeters away. Each mass of the arm is 5.5. The skater is initially spinning at some speed, draw their arms into their body to this new distance of r, and which is 15 centimeters, and what is their final angular speed. So first we want to make sure we understand why this is an angular momentum problem at all. Normally momentum problems are two objects or more objects interact, transfer momentum, and then we use conservation of momentum to study that. But of course there's two reasons why this could be confusing. One, it's not clear that there actually is more than one object here. There's just a skater. But actually the entire system is made up of three objects, right? 1, 2, 3. So this is like three objects interacting by the changing of the lengths of the skater's arms. And of course it's not linear momentum because the center of mass of the skater is not changing, but they are spinning around it. So that's how we know it is an angular momentum problem rather than a linear momentum problem. So let's get started and see what we can do here. So the first part of this problem says, what is their initial moment of inertia? So what is their moment of inertia before they start spinning? But before they start pulling their arms in, they are currently spinning. So we just need to add the moments of inertia of each object. There are three objects, two arms, and one cylinder. So the total moment of inertia will be the moment of inertia of the body plus 2 times the moment of inertia of the arms. So what's important here is just to remember that when you find the total moment of inertia, or when you want to add up the angular momentum of a bunch of objects, you want to add the moments of inertia, the i's. You don't want to add the m's. The reason you want to do that can be seen from the very next line, which is, and actually before I do that, I want to label the variables of the problem. So we've got labels for m, the mass of the arms, the radius of the arms, initial and final, but we don't have labels for the mass of the body, so I'm going to call that big M, and the radius of the body, I'm going to call that big R, and I think we have labels for everything else. Okay, so now going back to my moment of inertia, if the body is a disk, that has a moment of inertia of 1/2 mr squared, and then I have two copies of the moment of inertia of the arms. The arms are points, they act like hoops with moment of inertia mr naught squared. So that's exactly why you don't want to just add the m's, because each m is associated with a different shape and a different constant in front. Single points are associated with a 1 right there. There's 2 of them, so there's a 2 right there. Disks are associated with the 1/2. So if you just added the masses, you'd be adding different numbers in front and you'd get the wrong answer. Okay, so if I just plug this thing into my calculator, and I'm going to label it as I with a little I there to be initial, because that's before they draw their arms in, and I get 1.765, and the units on that is kilogram meters squared per second. Cool, that's part A. So for part B, I want to actually do the conservation of angular momentum problem. I know what their initial speed is, then they draw their arms into the body to a radius of r equals 15 centimeters. So conservation of angular momentum looks a lot like conservation of linear momentum. Change in L is 0. This is a rigid object, so I want my L to be represented by I times omega. So delta L equals 0 means LF minus Li is 0, which means that IF omega F minus I omega I is also 0. So I know some of this stuff already. I know II right there. Omega I is 3 revolutions per second, so let's quickly convert that into radians per second. So 3 revolutions per second. Converting that is a matter of multiplying that times 2 pi, and that times 2 pi is 18.8 radians per second. The unknown thing I'm looking for is the final speed, final rotational speed, so I need to figure out what IF is. So that's not going to be too bad because it's exactly the same arrangement of objects, but now the radius of their arm is shorter. So I just need to change this radius to that radius. So let me just write that down. I final will be, again, 1/2 mr squared plus 2 m, and now just times r squared. If I plug that into my calculator, I end up with 0.6651, again, kilogram meters squared per second. So now I know everything in my conservation of angular momentum formula but omega f, and so I can solve for omega f. So just taking this formula and rewriting it, I get IF omega f is II omega I. Divided by IF, I get omega f is II omega I over IF. If I plug in the numbers for this guy, I get 50 radians per second. So that sounds like kind of a lot, and it is like kind of a lot, but it does make sense because I started out at 18 radians per second. I pulled my arms in and sped up a bunch because I have less moment of inertia. If the moment of inertia goes down, that means omega has to go up, and I get 50 radians per second. Cool. Okay, so let's take a look at part C. So part C is trying to say that, okay, momentum conservation is a nice picture to study mostly what happens to this system, but of course, like, because of the interaction between the ice and the skates, there is some friction that happens there that will slow down the rotation of the skater, which I'm sure you could have guessed already. So now we want to try to take that into account by saying that what slows the rotation of something, well, that's the torque. And remember, we label that torque as tau. And the spin takes 3 seconds. That's 3 seconds between the time when the skater starts to spin and they finish spinning. And I want to know, with some torque, how fast are they actually moving at the end of this time period. So I expect the speed will not be as large as this one, but it will certainly be larger than the original 18.8. Probably, I guess it's possible there could be enough torque for it to slow down beyond this, but that's not really what we expect because that's not what we actually see. Okay, so how are we going to do this? Well, the formula that relates torque to angular momentum is torque is the change in the angular momentum over the change in time. So I put vector signs above that. To actually do the directions here, we would have to do the right-hand rule. So let me just do that real quick. So let's say the person is spinning in that direction. So that means I take my right hand, I curl it in the direction of that green arrow, and I get that the angular momentum is pointed upwards. So I'm going to call that upwards direction the z-hat direction. So then I can rewrite my torque expression in the z-hat direction. So this is going to be torque z, delta LZ, delta t. So what do we expect is going to happen to delta LZ and to the torque in the z direction? Well, we expect, this is the initial, we actually expect L final to actually get bigger than the initial, right? That's because the arms are coming in, the speed is going up. So we actually expect LF minus Li to be a positive number, right? We expect the final to be greater than the initial. Well, when the torque is applying, when it's slowing down the angular momentum of this system, actually the torque should be in the opposite direction of Li, right? I mean, when you apply a torque, you reduce or increase the moment of inertia, and for a frictional torque, you are definitely slowing down the moment of inertia. So the key point I'm trying to get at here is that although our torque here is 3.5, when we put it into this formula, we want to put a minus sign in front of that Tz. So what I'm going to say is Tz, that is the torque in the z direction, is going to be minus that constant 3.5 because it needs to slow down the skater. In reality, that torque is actually in the opposite direction as Li. That's actually the direction of the torque vector. Again, that's using the right-hand rule, so it's a little beyond where we need to be, but we can look at this picture and sort of see that's what's supposed to happen. Okay, well, the next steps are pretty easy. We just need to apply what we know about delta L and to this formula. So that's the left-hand side. Delta T is just tau. LZ, delta LZ is IF omega F minus I omega I divided by delta T. First thing I'm going to just do is multiply times delta T to get it off of the denominator. So that's minus tau times delta T is IF omega F minus I omega I. And again, we're just looking for the final speed, so move this guy to the other side and divide by IF, which is just that. And you can see in this form, it's easy to recognize that that negative sign should be there. You start with the angular momentum, the initial angular momentum. It is decreased because of the action of the torque. The torque is slowing down the final angular momentum. And then you divide by the final moment of inertia, and of course that slows down the final speed too, because if this is bigger, the final speed will be less, but this is just whatever we need to plug in. So now we just plug in all the stuff we know here, here, and here, and put that in my calculator, and I get 34.2. Okay, cool. So indeed, it was, significantly slower than here, but still quite a bit faster than this. You get about twice as fast instead of nearly 3 times as fast if you don't consider torque. Okay, great. So that's the end of this problem. The major lesson here is you remember conservation of angular momentum, which is this. This is for objects, starting with some initial angular momentum and ending with the same angular momentum, but the moment of inertia and speed can change in between. And so that's part of the lesson here, is that either I or omega could change, and either one of those will result in a change in the other. And we have the simple picture here of complete angular momentum conservation, that is delta L equals 0. And then we have the more complicated picture where there could be some torque, which means the angular momentum is not completely conserved, but if we know what the torque is, we can still do the problem and figure out how fast the object is really moving by including external interactions like friction. Okay, great. That has been a solution to a real-life skater. Thanks for watching. I will see you next time.